and with a bachelor's degree in software engineering. He used to write software for banks, and because of that, he really doesn't trust banks anymore. So that's why he works for Aeternity. So please welcome Dimitar Ivanov.
There you go.
Yep.
I'm going to need it. So, well, I'm Dimitar from the core team, and as Uf had already explained to you how channels work, that would be an easy talk. So, we're going to talk about channels. We'll make a brief introduction how they work with regards of what we're going to talk after that. We'll give some real-life examples, then we'll inspect how the WebSocket API works, and finally we'll talk why keeping your state actually matters. So, Douglas Adams actually puts this on the cover of the Hitchhiker's Guide of the Galaxy so people don't panic. And it's also because it's a bit complicated. And if channels do seem complicated, don't worry, don't panic. Everything is going to be all right. If you have to take one thing from this talk, is that all channels APIs are really well documented to have a few thousand lines of examples, and you can actually play with that. So please don't panic and follow me in the rabbit hole. Usually, when we're talking about the blockchain, we consider everything to be trustless and decentralized, and there are a lot of blockchain projects out there that are either trustful or centralized, and this is not the case with eternity state channels. They are decentralized by design, and as you would see in a moment, they're really trustless. Uf had already talked about the soft real time. So when you go to the coffee shop, your coffee won't be dry, cold, and useless. Channels have, since being state channels, they have a state that contains smart contracts, and those smart contracts are really powerful, and you can use them for either off-chain data, but they can also read on-chain data. So imagine that you're having an oracle that reports the weather in Prague. Actually, you can use that on-chain data in your off-chain contract, so you can progress your contract further. Being off-chain, both parties execute the smart contracts, so they're equal in that regard of consuming electricity for running the contract. So nobody pays fees, nobody pays gas. It's really cheap. The only fees you pay is opening the channel, closing the channel, and if you have to make some dispute on chain. So they're really, really cheap. Basically, you pay a few transactions and you can have 1,000 million or whatever off-chain transactions that come free for you. You only pay for your electricity and your network. They do have drawbacks. Currently, channels are only two-party entities. There's only Alice and Bob. There is not Alice, Bob, and Carol. But as we've already talked, this is about to change with the introduction of virtual state channels. Channels make steps further with updates, and each update has to be finished before the other one starts. So there are no parallel updates. And since channels are computationally bound by your CPU, it doesn't make much sense to have parallel updates in the first place. This is not going to speed your channel's progress anyway. We've already talked about on-chain confirmation. So if you go to the coffee shop and you don't have already opened state channel with the coffee shop bartender, you have to wait for that to be confirmed enough times on-chain, so you're safe to start making off-chain transactions. So real-life examples, I've divided them into good and bad. So turn-based games like chess or blackjack are really good because you make one move, the other party makes move, you make two moves or whatever. You can have insurances. So if I'm growing crops, let's say, and there is a hailstorm that actually destroys my crops, and I want to claim my insurance money, tokens, I can do that. And none of this ever touches the on-chain. So I both am safe, cryptographically safe, and I don't have to pay all the fees that I have to post the transactions on-chain. It's a similar issue with the betting. So let's say there is a football game that England and Germany are playing a match, and I want to bet for one of the teams, and for some reason I don't want this to land on-chain, and I can do that in a state channel, and it's going to be faster, but yet keep the same amount of safety I have on-chain. Other good example would be paying for video articles on demand. Like you pay just for a tiny bit of information. If you want to keep going, you pay for another piece of information, small amount. You don't pay for the whole thing if you don't need it really. But examples would be non-turn-based games. So if you're to implement, I don't know, StarCraft protocol in the state channel, it's going to be a mess. All issues that actually require more than two parties are really not a good fit for state channels. Like ICOs are not really good. Voting is definitely not a good fit for state channels. So basically, if you're developing an application for the channel, you need to know what the channel can do for you. So there are on-chain transactions, there are off-chain transactions. You don't produce them. The cat we've had a minute ago would actually produce them for you. You just need to code the correct API, and the FSM has your back. So you don't need to worry about that. What you need to know is that you have to create a channel in order to use it. You can add more tokens. You can take tokens out while it is still running. There are ways to protect yourself from being cheated even if you're offline, and you can close the channel. While the channel is open, you can send tokens to the other party, you can create smart contracts, you can call them. It's cool. So, bear with me. Basically, we have Alice and Bob, and they have phone applications. And Alice has a node, and Bob has a node. And Alice node talks via WebSocket to Alice's application talks to her node via WebSocket, and so does Bob's. And the two nodes actually talk to each other with noise session. So let's have the simple example where Alice sends Bob one token off-chain. We've already talked about this, so I'm going to be rather quick. So she says to her node, I want to send Bob one token. Her node takes that request, processes it, produces a new transaction, and sends it to Alice. Alice receives that, takes a look at it, because she's smart, she doesn't trust her node either. By the way, there are a lot of negative cases in that scenario, and I'm not even touching them. We're following just the happy path. So Alice likes the transaction, signs it, and gives it to her node. Her node checks that this is the very same transaction, checks Alice's signature, and sends it to Bob's node via the noise session. Bob's node notes that there is a new incoming update from Alice, checks the transaction, checks it is a correct one, checks Alice's signature, and sends it to Bob. Bob now is notified that there is a transaction incoming from Alice to him. He can decide if he likes it or not, and if he does, he signs it and gives it back to his node. His node again checks that this is the very same transaction, that Bob hasn't made the mistake, checks both signatures, and if done, sends it to Alice node. Alice node on her side checks that the transaction is the same, checks both signatures, and decides that this is okay, now we're safe, and eventually informs Alice. So don't panic. We actually don't care about most of this. What we care is that this part, the WebSocket connection between Alice and her node. If you're writing a state channels application, all you care is about this. Everything else is handled for you, and you're safe. So we have a simple API. This is a really hard concurrency problem that we're dealing with here, but actually it is all reduced to a simple sequence of events that you have to handle, and you're safe. For order to have constantly running incoming updates and outgoing updates, we actually persist the WebSocket connection to the node. So if Alice makes an update, Bob is informed for that. We wrap this in JSON-RPC calls, and the FSM knows how to do those. A small remark about the JSON-RPC is that it's beautifully abstracted, so you can actually easily replace that with any adapter if you like. So if you really want to go Kafka or something, you can really easily do that. So JSON-RPC is pretty standard. You have an ID, and basically you're making requests and you get a response. If you provide an ID, this will make the request asynchronous. If you don't provide, it's going to be sync. The other way around. So if there is ID, it's async, otherwise it's no. Okay. Okay then. So you provide an ID, you get the same ID, so you can reason about the message you received. You provide a method that says get me the balances of these accounts. Basically, you have a method and params you execute upon that method. So you get the result that has those accounts, and those are their off-chain balances. So what the FSM had done for you already is it looked through the state channels Merkle Patricia tree and extracted those accounts, got their balances, and produced them in a big, nice JSON for you. So what an off-chain update is actually. It's a multi-step thingy where one party, Alice, initiates, then Alice has to go out, so authenticated. She says, I agree with that. Small remark about authentication and signatures. Since we now have generalized accounts, it's authenticate, not sign. Authenticate means that it is either signed or authenticated via generalized account smart contract call. So then Bob authenticates the same thing, and they both receive that what the new state of the state channel is. So it's quite simple actually. The don't panic is real. The channels update new creates a new update. So Alice says, I want to transfer one token from that account to that account off chain, and that's it. Her node reads that, prepares a transaction for her, and informs her what the transaction would actually do. So she can check if this is what she really intended to. Then she signs it, and that's it. Now it's Bob's turn. Bob receives an update acknowledge message that has the same transaction, the same updates, and Bob can make an educated decision if he likes it or not. If he does, he signs it and gives it back to his node. Then the update is done, and they both receive what the latest state is. It's pretty simple. Then we have the on-chain updates that are pretty just like the off-chain ones, but then you have additional step where you can wait for enough confirmations for the on-chain. Basically, Alice starts the update, so signs it or authenticates it, then Bob authenticates it. They both receive the now new on-chain state because this is going to be posted on-chain, and then have to wait for enough confirmations to be mined on top of that transaction. Once this is done, they can continue making new updates. So what is common in both cases that we produce a new off-chain state, and it's really important to keep that. Well, the node keeps it for you, but you don't need to trust your own node to keep it for you. You need to keep it on your phone and maybe redistribute it to other sources to keep it for you. The thing is that if you lose that state, you're in trouble. If you have it, and even if your node dies, you can open the same state channel from a different node with that state, and you can continue from then on. The idea is that losing the latest co-authenticated transaction is like losing your private keys, basically. So you need to keep that. So as a client developer, you have to consume the API and keep the state. Basically, that's all you have to do. So, thank you.
Right. Let's have some questions. Whoa.
No.
Okay, go first.
Okay, so I have a question about this forced forwarding, right? Forced forward. Progress. Oh,
okay.
Yes. Because if you do it, you need to pay actually for all the gas from the contract that has been run, right?
Yes. What you do is take the off-chain contract, put it on chain, execute it on chain, and you definitely have to pay the price for that.
Okay. So what if, for example, Alice plays some game with Bob, and suddenly Bob realizes that he's going to lose, and of course they're playing for money, and in this case Alice is going to force progress it on the chain, right?
Yes.
And pay for the gas. But what if the gas price actually is so big that it is not worth for Alice to do? Is it a way to defend from this kind of situation?
It's a matter of balance. So in that case, the gas price is going to be that big that you cannot actually, it's going to be cheaper for you not force progressing. So you either use bigger stakes in the contract, so it's worth for you to force progress it, or if the stake is that small, you really don't care.
Okay, but what if, for example, Bob artificially performs some crappy computations that will raise up the gas price? Or is it just
It's always Bob.
wrong something with the contract?
You're talking about broken contract that actually is unable to be forced progress on chain? Well, then Alice shouldn't have agreed to using it in the channel in the first place.
Okay.
I've followed this community app that tried to build this payment channel, and this was like someone who completely came new into the ecosystem, and they run into several problems. Can you maybe recap a little bit from your position what was their biggest challenges, and also what your team has learned out of this?
Oh, so this is a multi-level question actually. So we're developing this API with the intention to be used, but since this is the very first application that is actually built on top of state channels, we're finally getting some real-life feedback. So, for example, an issue we had, for example, was that we really relied on having a persistent WebSocket connection all the time, which sadly is not the case in a web environment, where the user actually refreshes their page and suddenly there's no connection. On the other hand, I'm going to say the dirty word. There is a chain of applications that are built in order to build the application. So there is the node, there is the FSM, then there's the SDK on top of that. And changing one actually requires changing in the other. So this is more or less a process that we must optimize somehow. So this was extremely important for us to get this feedback, and they did a great job with the application. And it was really a great learning experience for us.
Right. Any more questions? Yeah. Go on. Good.
Hi. Is there already some way of measuring when the state channels with their state become, just so to say, too stateful to dispute on mainnet? Because as far as I know, we don't have a dispute mechanism that would suit for arbitrarily large state channels yet.
And the restriction you would have are produced by two things, basically. One would be the size of the state you want to post, and the other is the computational complexity of the contract call you want to call. So basically, this probably is a really good fit for client-side computations to be made. You know the state, you can compute its size, and you can make some heuristics about the gas price needed for certain calls.
Yeah, is that answer? Okay, one more.
Yeah. What's your plans for versioning the JSON-RPC API?
Well, we can support different versions. That's the thing. We have abstracted away the adapter basically, so it can be, we can have as many of those as we'd like, and they will all fall back to the same FSM. And the version of the adapter is not bound to the FSM itself, so we can have really modular system that we can build on top of. Well, once we're still in version 1 of the API, basically, and since we're still gathering feedback, probably once we say, okay, this is enough for this version, now we start producing a backwards incompatible version that changes everything. Let's say beta.
Okay, I think let's give a round of applause to Dimitar. Thank you.